All right, thank you for the introduction. So for the last two lectures, we were discussing local concepts of endoscopy, first for quasi-split groups, then for general groups. And today we're going to head back to the topic of the first lecture. In the first lecture, we discussed the stabilization of the regular elliptic part of the trace formula for SL2. And today we're going to do the same thing, but for a general reductive group, the regular elliptic part. No black markers, so we'll do blue. Okay, so. All right. So what is a strong irregular elliptic part? Well, we're going to be summing over, this will be my notation, SR for strong irregular, ELL for elliptic, up to conjugation, and then we'll have a volume term, just like in Ali's talk. And then we have the orbital integral term, where here T is the centralizer of delta in G, and for G itself, connected reductive over F, F number field. We can just take it to be Q if we like. And so if you remember our approach, the first thing we did for SL2 was to group it from usual conjugacy classes into stable conjugacy classes over F. So this is what we're going to do. The first observation is if delta, delta prime in G of F, strongly regular, are stably conjugate, then we have, in fact, a canonical isomorphism between their centralizers. We called it phi delta delta prime from T delta to T delta prime over F. The volumes are therefore the same, so we are going to regroup into a sum up to stable conjugacy. The volume term will remain the same. And then we're going to sum within each stable class the individual rational classes. So conjugacy classes which are stably conjugate to delta. Okay. And so the next step for SL2 was to recognize that this sum here is not a stable distribution, because this is the orbital integral is adelic, and if we want to have a stable distribution, we should be summing over the adelic conjugacy classes that are adelically stably conjugate to delta, and not rational conjugacy classes. And so last time we introduced the Galois-theoretic parametrization of rational inside of stable conjugacy. So let me introduce a little bit of notation now. We were so far only dealing with fields, but now we're also dealing with the adels. So I'm going to introduce the following notation. I believe it goes back due to Tate. So H1FT, this is going to be H1 of the Galois group of F bar over F. And the module is T of F bar. Then we have H1AT. This is going to be, again, H1 of the Galois group of F bar. And in fact, it doesn't have to be 1. It can be any I. But now the coefficients are T of A bar. And then finally, HI A over F T, where the coefficients are the quotient T of A bar over T of F bar. Okay, so this will be my notation. And then, so what are we looking at? Well, from last time, we know that the kernel of the following map, this parameterizes this summation set here, the rational conjugacy classes inside of the stable class of delta. On the other hand, we want to switch to the adelic classes inside of the adelic stable class of delta. Those are going, oh, I wanted to write F here. Those are going to be parameterized analogously by the following kernel. By putting together the information from all places. And so we're interested in the following natural map. Okay. And so in the example of SL2, a few special things happened. One special thing was that H1FG was trivial, and so was H1AG. So really, this map was just from H1FT, oh, thank you, to H1AT. The second thing that happened was that this map was actually injective. And then we'll talk in a second later about here. And so this also fails in the general case. So in the general case, we have to worry about these kernels, and the natural map is not injective. What happens if we have two elements here that fuse together in here? Well, the corresponding orbital integrals are then going to be equal, because that means these are two rational classes which are stably conjugate to each other over F, but actually become adelically conjugate to each other. They belong, even though over F there are two different conjugacy classes, adelically they're the same conjugacy class, so the orbital integrals will be equal, and so we can factor this out. So our sum will now become the sum over delta, the same, volume term stays the same, and then out here I can take out the kernel of alpha, and then I'll be summing over the image of alpha, A inside of the image of alpha. And here I'll have the orbital integral A times delta of F. What does A times delta mean? A times delta is the delta prime such that the invariant delta delta prime is equal to A. Okay, so this is where we are. But now, the next thing we did for SL2 was to extend from the image, from summing over the image of alpha, to summing over this entire group, because this is what you need in order to get a stable distribution. You need to sum over all adelic classes within a given stable adelic class in order to get an adelically stable distribution. So what was it that came here? It was this, and this was isomorphic in our example to Z mod 2Z. And so we recognize that we're summing over this subgroup of this group. We wanted to sum over the whole group. There are two cosets, and the way we did it is we summed over both cosets, but then we have to subtract the error that we were doing, that we introduced by doing so. And so let me introduce a little bit of more notation in order to make my life a little easier. I'm going to say Ker1 FH for any connected reductive group H will be the kernel of this map here. So that will be the kernel. It will be the kernel of the vertical map. The kernel of H1 FT or FH, really now, into H1AH. Okay. All right. And so the map alpha that we're now looking at goes from Ker1 FT to Ker1 FG. So the goal now is to understand how can we replace this group here in general in order to kind of make a similar analysis to in the case of SL2. And this is easy to understand when the group G satisfies the Hasse principle. So the next steps are called pre-stabilization. And the first part of pre-stabilization is going to be when G satisfies the Hasse principle. All right, so here's the definition. G satisfies the Hasse principle if Ker1 Fg is trivial. Right? In other words, the natural map from the F cohomology to the A cohomology is injective. All right, so, well, when that is the case, we're going to do something very similar to what we did here. What did we do here? Many groups G satisfy this. Simply connected groups satisfy this. Adjoint groups satisfy this. Classical groups satisfy this. It's a little bit, it's very easy to find reductive groups, or even more specifically tori, that fail the Hasse principle. It's kind of tricky to find semi-simple groups that fail the Hasse principle, but those do exist already in type A, but you have to work a little bit. Okay, so what did we, let's look a little bit more formally what we did here in the case of SL2. We had these two cosets here, B0 and B1. B0 was the image here, B1 was the non-trivial coset. We're summing over B0. We said we'll sum over B0 and B1, but then we're going to take away our sum from B1. So this is addition and subtraction. So what we're going to do now in the more general case is what Drinfeld one jokingly said to me is the scientific word for addition and subtraction, namely Fourier transform. And so here is an exercise. Let's say you're given an exact sequence of abelian groups. And C is finite. And you have some function y from B to C, which is finitely supported. Then the sum of the values of this function over the group A is the same as the following sum, where you're first summing over characters of the finite group C, and then you're summing over all B's in B, kappa B, YB. Okay, so that's a simple exercise for you. So now the question is, find C in our case. What is our case? In our case, B, in our case, the map here is the map alpha, and we're replacing A by the image of alpha. Okay, and so when C satisfies the Hasse principle, it is going to be very easy to find C. But what is the condition? Of course, we need to have this sequence exact, so let me spell out the condition. The condition is an element A in the kernel of H1 AT to H1 AG maps to 0 in C if and only if it lifts to the kernel of H1 FT in H1 FG. And so here is an obvious exercise for you. If G satisfies the Hasse principle, then we can take C to be H1 A over F T, just like we did in the case of SL2 here. This need not be Z mod 2Z anymore, but I should say this. So this is one of arithmetic results. H1 A over F T is finite. It's always a finite abelian group. So it meets, Oh. Right. Whoops. This is no good. This is... this is what the alpha that I... Let me... I'm not sure what this is an unfortunate collision of notation. So this map, this kernel is the kernel of this map. So I think this is the map alpha. I don't think I used the other map alpha anywhere. So let me, I don't know if why did I use this? Okay. All right, and so then, now, we can just use this exercise, and so what we get is the sum over delta 0 in G of F strong irregular elliptic up to stable conjugacy. Here we have the volume factor, and then we have the kernel of alpha, and then by this exercise over there, we have the size of H1 A over F T inverse the sum over kappa, which are characters of this. And then now, not enough room here. Then the next sum goes over over this. Then we have kappa of A, orbital integral of A delta 0 F. Okay, and so now this is the end of the pre-stabilization in the case of Hasse principle, because now so we can call this, just like we did for SO2, this is the kappa orbital integral for delta 0 of F. And when kappa is equal to 1, orbital kappa delta 0 is stable. This is the stable orbital integral of delta 0. And then the other ones are going to be related to endoscopic groups. But before we do this, we actually want to remove the condition of the Hasse principle. So the next step, we pre-stabilization two, so there will be no Hasse principle. Okay, so when we stop using the Hasse principle, it turns out that this group is no longer the right group to take. So we have to modify this group a little bit. And the first step, well, but there is something that does satisfy the Hasse principle, namely every simply connected group automatically does. So the simply connected cover of the derived group satisfies the Hasse principle. So this is a theorem due to Harder, Kneser, and Chernousov that says GSC satisfies the Hasse principle. Okay, so we're going to use this theorem, but we're going to need the following fact, namely two strongly regular elements, delta and delta prime, in G of A are G of A bar conjugate if and only if they are conjugate under the A bar points of the simply connected cover. So this is not immediate. In the case of a field, of course, it is immediate, but in the case of the Adels, this is not immediate. So let me make a little remark. The natural map from GSC A bar times center A bar to G A bar. A bar, the Adels of F bar. No. Okay. This map is not surjective. However, there is a little lemma of Kottwitz that still tells you that what you want is true, namely, but Kottwitz tells you that for almost all W places, we have that GSC of OW times T of OW is G of OW. Have to take a finite, there is a finite Galois extension such that this is true for almost all W. And that's what you need in order to make this work, and then that gives you this fact. Okay, so, I'll put it in the notes. I don't remember the title off the top of my head. All right. Well, what does that give us? That actually gives us a refinement of the cohomological invariant. So remember, we have the invariant delta 0 delta. This is going to be in H1 AT when in the situation that we're in here. The delta is stably conjugate to delta 0, and here we were calling this A delta 0. That was our delta. Say again? No, I do mean T. I do mean the centralizer of delta. Or delta 0, if you like. Yes. So maybe I should say one of these has to be rational. Although, no, actually, no. No, it can be an adelic point. If it's an adelic point, T will still have, the centralizer will be integral for almost all places, so that this is still fine. This is, so we had the invariant for two stably conjugate elements, and how was it? It was represented by G inverse sigma G, where G is an element in A bar, G delta 0 G inverse is delta. Now, the fact that actually we can conjugate this element over GSC, this is going to give us a refined invariant. So we get a refined invariant SC delta 0 delta in H1A TSC, where TSC is the preimage of T in GSC, exactly by the same formula, but now you take G to be in the simply connected cover. And we're going to use this refined invariant to get our hands on the appropriate definition of this group C that we're looking for. Okay. So namely, this is what, and what does refined means? So under the natural map from H1A TSC to H1AT, the refined invariant maps to the odd. That's obvious. Okay. And so now here's the definition for the new group C. All right, so first of all, we're going to define delta to be the image of the following intersection: the kernel of H1A TSC to H1AT. How do you make an intersect it with the kernel of H1A TSC to H1A GSC? So we're going to intersect these two subgroups of this group, and we're going to take the image of that intersection under H1A TSC to H1A mod F TSC. So this is going to be my delta. It will be a subgroup in here. And so I'm erasing the exact condition that I would like to satisfy, unfortunately. Well, or maybe if I don't satisfy it, you won't notice because the condition has been erased. But the exercise is the following. The original invariant, delta 0 delta, which was in this kernel of H1AT to H1AG, lifts to the kernel of H1FT to H1FG. This is the condition we wanted to satisfy if and only if the image of the refined invariant, delta 0 delta, in H1A mod F TSC lies in delta. Okay, I realize that I've written this pretty quickly, and you're looking at this and you're saying, what the hell is going on? But actually, it's an elementary calculation that I'm going to leave as an exercise for you. It's just simple diagram chasing in Gauss cohomology. But if you believe this exercise, then now you know what the correct definition of the group C is that we want. Namely, we're going to define, and it's not really called C, it has a traditional name. It's called kappa T over F dual. Well, usually in the traditional texts, one first defines this and then dualizes it, but I find it more illuminating to define it on this level instead of the definition usually given in terms of the dual group, which seems a little unmotivated if you see it for the first time. So we're going to define this to be just the quotient of H1A mod F TSC by this subgroup delta. And why did we define it this way? Because then, and we're going to define an element ops delta. Ops will stand for obstruction, and you'll see in a moment why obstruction is a good name for it. to be the image, well, let me just say it more simply. Image of this refined invariant in this group. Okay. So this is going to be our group C. So now we can apply the previous exercise to come to a very similar, maybe I'll leave this here as a comparison. Maybe let me first, I want to make a little remark. I'll make the remark here. In fact, we use this invariant, but we could have also, in hindsight, used the old invariant. Namely, there is a natural map from the kernel of H1F, AT to H1AG. This is where the old invariant lived, to this group, kappa T over F D. And the old invariant maps to this obstruction. Okay. So the refined invariant was used as it's used internally both as a motivation and also to solve this exercise, but really the obstruction can then in hindsight be taken as the image of the old invariant. And so now the pre-stabilization becomes the following. As before, we're summing over delta 0 strongly regular elliptic elements up to stable conjugacy. We have the volume factor. We still have the kernel of alpha. And now we have the size of this kappa group that we're using for the Fourier inverse. Then we're summing over all kappas in kappa. And then finally we're summing over, I could either write it like this over A, or I could write delta in G of A, strongly regular elliptic up to A conjugacy, and delta stably conjugate over A bar to delta 0, and then we have kappa of obstruction of delta orbital delta of F. And then there is another Galois cohomological computation that tells you that this here is the Tamagawa number of G times the Tamagawa number of T inverse. So these somewhat technically looking terms actually combine together to something very nice. Okay, so we're almost done with pre-stabilization, Yes. Sorry? Well, I'm taking the Tamagawa number, the Tamagawa measure on T. Who, G or T? So where should, so what the problem is here? But I still have the Tamagawa measure on T. That is fine even if T is GM. Yes. But I'm taking the volume with respect to the Tamagawa measure. Yes. I understand. But isn't that what the Tamagawa measure is doing? It has the local components exactly so that the volume of this is by definition a Tamagawa number, which will be 1. I'm taking the volume with respect to a measure that would give me volume 1 of GM. then the tau of t is going to cancel against this volume, and I'm only going to have a tau of g. It depends on the measure you're taking. Okay, I think we're talking about we're talking past each other, but so I think it's okay. This is going to go against this. Okay. All right. So the next step would be to, well, when kappa is trivial, this is going to be the stable orbital integral. When kappa is non-trivial, this is supposed to be related to an endoscopic group. But this relation is going to go through the local transfers that we discussed in the previous 2 lectures. But before we can do this, we actually have to switch between stable classes in G and stable classes in the quasi-split form. So this is what we're going to do now. So this is pre-stabilization 3. Stable classes in G0. So I'm going to take G0 to be the quasi-split form of G, and I'm going to take psi from G0 to G to be inner twist. Yes. Yes, I'm using the Tamagawa measure for any global group I have. Is that true, or is that true up to some concept? I'm not sure. I'm only asserting it here, but it's a simple thing to check, but I don't know it off the top of my head. If when G satisfies the Hasse principle, this group literally coincides with kappa TF. Or it's sufficient to do the pre-stabilization. It could be off by a useless factor, and I don't have it in my head at the moment. I don't know. It's because it comes, I mean, that's the thing that has a signal value somehow when you write a trace formula. There is a volume factor. Okay. So what this gives you, there is a correspondence between stable classes in G and stable classes in G0, because stable classes are, after all, just F bar conjugacy classes, and this is an isomorphism over F bar. But we do need to do some work. So we have an obstruction. What does it measure? So given delta 0 in G of F, delta in G of A, stably conjugate, obstruction delta vanishes. I'm just reformulating the exact sequence A, B, C and its meaning. Obstruction vanishes if and only if the GA class of delta has an F point. And this is why this is called an obstruction. It's the obstruction to the existence of an F point in the GA class of delta. So we need to refine to the case where delta 0 is now in G0 of F and delta is in G of A. Because we're going to be summing over stable classes in G0. And the refinement is, so first of all, it turns out that the group C or kappa that we introduced is good enough. It's just the same group in both cases. But the construction of the obstruction is a little funnier, because this construction of the obstruction here used the invariant. When you have two elements that are conjugate under an A bar point of the group, there was this cohomological invariant, either this one or the previous one, Well, now, because we're going across an inner twist, this invariant doesn't make sense. So and in fact, the whole previous lecture that I talked about, its whole purpose was to make sense of this invariant. That's why I introduced these gerbs and all. Well, we didn't introduce them in the last minute or so. But that's why we introduced the concept of a pure inner twist and isomorphism. All of these things were there to allow for the definition of such an invariant. Well, it turns out that in the global context, you can kind of skirt the problem. And this is why the local problems were not taken seriously for a long time. In the global case, the problem somehow doesn't manifest itself too badly. So let me tell you, the construction is a little bit ad hoc. So here's the construction. Okay, so choose G in G0 A bar such that delta is psi of G delta 0 G inverse. This G exists by the very assumption that these two elements are stably conjugate. Let Z sigma bar be the one cocycle in the adjoint group. And here comes the funny part. Choose a lift U sigma of this cocycle to the simply connected cover, but you cannot ensure that it's a cocycle anymore. This cohomology class may not lift, so it's just going to be a cochain. Okay, then G inverse U sigma sigma G is going to be again a cochain in TSC of A bar. But the cochainness is gone. What is the cochainness? What prevents this from being a cocycle? What is the differential of this cochain? Well, it's something central. First of all, it's something central. But secondly, it is F rational. It's not a delic. It is rational because it comes from the differential of this, and this was just a rational cocycle. So now the image in C1 gamma of TSC A bar mod TSC F bar actually is a cocycle. And this cohomology class is the one we're going to use. So define ops delta to be its class in kappa T over F D. So this ad hoc, and this ops delta depends neither on G nor on U sigma. It's just independent of everything. And so now we're basically done. So again, we have the exercise, which says ops delta is trivial if and only if the GA class, conjugacy class of delta has an F point. Okay. And so now we just take this as it is, and we can replace delta 0 going over G with delta 0 going over G0, and that's the end of pre-stabilization. So what we now have is sum over delta 0 going in G0F, strongly regular elliptic over stable conjugacy. We have the volume factor, we have the sum over kappa, and then we have the sum over delta in G of A, strongly regular elliptic up to conjugacy, delta 0 conjugate to delta stably, O kappa delta, kappa obstruction delta orbital delta F. Oh, and I forgot, so the volume factor, the volume factor went, and now we have a Tamagawa number of G sitting here. So that's the end of pre-stabilization. The next step is to relate these kappa parts two endoscopic groups. We defined endoscopic data in the previous two lectures, and we also discussed the transfer identities that are needed. So now we can just use this. But what does it take to use this? Well, the transfer identities were defined in terms of transfer factors, whereas the pre-stabilization was in terms of this obstruction. So we need to relate this obstruction to the transfer factors that we introduced. So this is called transfer. Okay, so we're going to fix a particular summand in this formula. So fix T and kappa. From there, we're going to obtain an endoscopic datum as follows. This is, if you like, the initial construction of endoscopic data. Okay, in order to understand this, we need to understand this group kappa a little bit better. So Tate-Nakayama duality tells us that H1 of A over F TSC is isomorphic, or its dual is isomorphic to the following. We take the dual torus, divide out by the center of the dual group, take Galois fixed points, and then take the group of connected components. In fact, I could even forget the group of connected components because this is an anisotropic torus, but this is actually true in general. Now, what is kappa? Well, kappa dual was a quotient of this. So when we dualize, the dual of kappa dual, which will be just kappa, will be a sub. And under this Tate-Nakayama duality, we can actually see exactly what this sub corresponds to. And this is how kappa is usually defined in the papers on the stabilization of the trace formula. It's the kernel of the map that starts from here and goes to the product of H1 Galois V ZG hat. Okay, this is it. And Bill, so you had asked, are you going to motivate the property of the endoscopic element S in the global case? Something that was Galois fixed mod ZG, and then lifts locally everywhere for each place. This is where it comes from. Because the element S is going to be, well, it's going to be, it's the same as a kappa. It's a character on this group dual. That is, it's an element of this, so it has to, by its very nature, be in here. It has to be Galois fixed only modulo the center, and it has to be locally liftable for at each local place. This is where this comes from. It comes from what you need in order to create this obstruction. Well, so now, so thus, kappa is in particular an element of T hat mod ZG hat gamma. So now recall, we have a canonical G hat conjugacy class of embeddings. So in this way, this kappa becomes an element of G hat, or G hat adjoint, and we can take its centralizer. So let H hat be the centralizer of kappa in G hat. So now we have H hat, and we have S, and we have eta, which is almost what you need for an endoscopic group, but you of course need to say, well, who is the dual of H hat? You needed the H. This is a little bit technical, but So let RH inside of X, let's see, upper star T, which is X lower star T hat, be the preimage of the core-root system of H hat. After all, by its very construction, H hat being the centralizer of kappa, kappa sitting inside T hat is inside of H hat. The entire root system of G is in here, or the entire core-root system of G is in here, and H hat being a subgroup of equal rank, a centralizer of a semi-simple element, it has a subsystem, and we can take it here. It is Galois invariant because of this Galois up here. However, the Galois action does not preserve a base, but we can force it to do that. So for each sigma in Galois, there is a W sigma H in the Weil group. Omega will stand for the Weil group. T hat H hat, such that omega sigma H sigma. I have to, sorry, let me choose a base delta H in RH. Then there is a Weil element such that this preserves this base. And now I'm good. Now I have exactly what I want. A root system, an action of the Galois group on it preserving a base, so I get a quasi-split reductive group H. Okay. So we get a quasi-split reductive group H with, which root system RH. And, well, because time is closing in, let me skip another technical discussion and tell you that there is an embedding of T, this T that we started with, where did we fix it somewhere, into H, well-defined, over F, no less, well-defined up to stable conjugacy. So not only do we get an endoscopic group, but we get a canonical way to put our torus that we started with into the endoscopic group. Okay. So now we're in the situation that we have the transfer factors. So in other words, let's see. So for any delta 0 in T of F, we get gamma in H of F up to stable conjugacy. Okay, so now we're ready to relate the transfer factors from the last two lectures to the obstruction and apply the transfer identities to complete the stabilization of the trace formula. The first theorem that we need is the theorem of Langlands and Schellstadt. So let W be a Whittaker datum for G0 over F, now a global Whittaker datum. Then the product over all places of gamma V delta 0 V is 1. Okay, so now we're going to recall the property of the transfer factor, delta of W gamma V delta V, where now delta is the element in potentially the inner form G that is adelically stably conjugate to D0, to delta 0. That is going to be the transfer factor for delta 0 V times the invariant of delta 0 V with delta V. And then there was a way to construct, let me just write S symbolically, even though there was a way to transfer the S to where it needs to go. Well, if you combine this theorem with this property, what you get So let me say something verbally. Which transfer factor am I talking about here? Well, in the case when G is quasi-split, it's the usual transfer factor. When the case G is not quasi-split, it's the transfer factors we discussed last time. Well, they had to do with, in the general case, they had to do with this gerb that I introduced in the very end. Well, now in order to make sense of this globally, you need a global version of this gerb. But this can be done. You can put it in here, and then you have this statement. And then what you see is the following. As the almost immediate corollary, the product of the transfer factor for gamma V delta V, all these terms are going to become 1. This is going to be the sum of these invariants, delta 0 V delta V, paired with S. But S was kappa, and the abstraction was defined in such a way that it's the adelic packaging of these local invariants, at least in the quasi-split case. You have to again use the gerbs in order to make sense of this in the non-quasi-split case. I'll completely skip this, but I'll put it in the notes. And so this just becomes abstraction delta paired with kappa. Okay, we actually wrote it just a moment ago. It's just kappa applied to abstraction delta. See? And so what this tells you is that now you can take the kappa orbital integrals from the pre-stabilization. Where did they go? They also went. But they were there, I assure you. That tells you that the kappa orbital integral is the product over V of what? The sum of delta V in G of FV up to conjugation, transfer factor, gamma V delta V, orbital delta V FV, and then this here, by the transfer identity, becomes equal to the stable orbital integral at gamma V of FV. And so, thank you. And so that's the end of stabilization. So now what have we done? We have written our trace formula, regular elliptic F, as a sum over endoscopic data up to isomorphism. I did not talk too much about the concept of isomorphisms of endoscopic data. There is a certain factor here, IHG, and then the stable trace formula, G regular elliptic part of F upper H. And these factors in here, what do they encode? They encode automorphism group of the endoscopic datum, and they also encode Tamagawa numbers, the Tamagawa number of G and the Tamagawa number of H. The Tamagawa number of G was floating around in here, but and the Tamagawa number of H is somehow present in here, and in order to accommodate for them, you put them in here. So that's the end of the stabilization for the regular elliptic part. And next time, there will be a special treat. We're going to talk about the stabilization of the full trace formula for SL2, so that you see how terms that are not regular elliptic, so the hyperbolic terms, the unipotent terms, how they get handled and packaged, and it's going to be fun. It really depends on how you sum, right? So first you sum over delta, and then delta determines t, and then you're summing over all kappas determined by t. But instead of summing first over delta and then over kappa, you might as well first sum over the different t's, and then over kappa for each t, and then over delta that's associated to each t. So you just switch the order of the sum. No, so S does not see T because there will be different, all the T's that come from H will give you the same S. So there is a certain kind of combinatorial reshifting of the sum that I did not explicitly discuss. But more or less it amounts to just switching the order of summation of two sums. G regular elliptic, that's right. Elements, sorry. So first of all, the H is an elliptic, and I defined what an elliptic endoscopic datum is. We only sum over the elliptic endoscopic data. And then elliptic for G and H is the same, the concept of an elliptic element. No. So this is on H, but I only take G regular elements. This is very important because in the case of SO2, this will be a torus. Every element in the torus will be regular because it's an empty condition, but remember we're missing two elements, the plus and the minus one. So really we take G regular, and it's very interesting to see where these missing elements come from. They end up coming from the unipotent elements that we were not thinking about here. The unipotent elements give you the singular elements for the tori in SO2. So it's kind of fun, and then the other part balances out with a spectral contribution. So it's pretty neat. Yes. It is not important. So in order to make sense of what FH is, you have to extend this eta to an L eta, but this summand here is not going to care about that. Because if you change the L eta, then the FH is going to change, but something else is going to change, so it balances out. When? It's 2 o'clock. Next talk, 2 o'clock.
I think he asked, how do you know the volume is finite?
The volume is infinite. I think so. They're usually quotient by the z plus factor, the r factor. I mean,
well, you can do multiple, you can do different things, so you can intersect with G. No, the intersect with G of 1 is not going to help.
What you have in your mind is it was just the Tamagawa number.
The Tamagawa measure, that's right.
No. I mean, so what is the volume for which measure? It's an R measure divided by the counting measure. So it is infinite. You have to divide by some...
No, you have these local... So the Haar measure is a product of local Haar measures, and each local Haar measure is denominated by the Tamagawa convergence factor, so that when you put them together, you get a convergence.
So then it is not... I mean, so if you want to introduce... What are you looking at? This is it's completely...
I'm looking for... just looking around.
Just a matter of
just checking out.
Maybe I should not have written volume. Maybe I should not have written
Follow... What's that?
You should follow WeTech for lunch.
I think...
You should talk to WeTech about lunch.
Sure.
I mean, the volume of D cross mod F cross is infinite.
It's not a volume, that's the problem. It's not a volume.
No, in order to write a trace formula, you need that quotient to have finite volume. I mean, otherwise everything is like continuous spectrum. No, you mod that by like an extra central factor. I mean, that's what you do. It's always the same thing. I mean, they work. It's just like, I think it's a notational